on cryptocurrency. The Genesis block contains a hidden message within it. The Coinbase transaction input contains the text, "The Times, 3rd January 2009, Chancellor on the brink of second bailout for banks." This message was intended to offer proof of the earliest date this book was created by referencing the headline of the British newspaper The Times. It also serves as a tongue-in-cheek reminder of the importance of an independent monetary system, with Bitcoin's launch occurring at the same time as an unprecedented worldwide monetary crisis. The message was embedded in the first book by Satoshi Nakamoto, Bitcoin's creator. Linking blocks in the blockchain. Bitcoin full nodes maintain a local copy of the blockchain state starting at the Genesis block. The local copy of the blockchain is constantly updated as new blocks are found and used to extend the chain. As a node receives incoming blocks from the network, it will validate these blocks and then link them to the existing blockchain. To establish a link, a node will examine the incoming block header and look for the previous block hash. Let's assume, for example, that a node has 277,314 blocks in the local copy of the blockchain. The last block the node knows about is block 277,314, which is with a block header hash of, I'm not going to read all this out, it's too big, but you can see there yourself. The blockchain node then receives a new block from the network, which it parses as below. Looking at this new block, the node finds the previous block hash field, which contains the hash of its parent block. It has a hash known to the node that of the last block on the chain at the height 277,314. Therefore, this new block is a child of the last block on the chain and extends the existing blockchain. The node adds to this new block to the end of the chain, making the blockchain longer with a new height of 277,315. Figure 914 shows the chain of 3 blocks linked by references in the previous block hash field, Merkle Trees. Each block in the Bitcoin blockchain contains a summary of all the transactions in the block using a Merkle tree. A Merkle tree is also known as a binary hash tree. It is a data structure used for efficiency, summarizing and verifying the integrity of large sets of data. Merkle trees are binary trees containing cryptographic hashes. The term tree is used in computer science to describe a branching data structure, but these trees are usually displayed upside down with the root at the top and the leaves at the bottom of the diagram, as you will see in the examples that follow. Merkle trees are used in Bitcoin to summarize all transactions in a block, producing an overall digital fingerprint of the entire set of transactions, providing a very efficient process to verify whether a transaction is included in a block. A Merkle tree is constructed by recursively hashing pairs of nodes until there is only one hash called the root or Merkle root. The cryptographic hash algorithm used in Bitcoin's Merkle trees is SHA-256 applied twice, also known as double SHA-256. When n data elements are hashed and summarized in a Merkle tree, you can check to see if any one data element is included in the tree. At most 2 log 2 to n calculations, making this a very efficient data structure. The Merkle tree is constructed bottom up. In the following example, we start with 4 transactions A, B, C and D, which form the leaves of the Merkle tree as shown in figure 9.2. Okay, the transactions are not stored in the Merkle tree, rather their data is hashed, and the resulting hash is stored in each leaf node as HA, HB, HC and HD. HA, SHA256, SHA256, transaction A. Consecutive pair of leaf nodes are then summarized in a parent node by concatenating the 2 hashes and hashing them together. For example, to construct the parent node HAB, the 2 32-byte hashes of the children are concatenated to create a 64-byte string. That string is then double hashed to HAB, SHA256, SHA256, HA plus HB. The process continues until there is only one node at the top, the node known as the Merkle root. That 32-byte hash is stored in the block header and summarizes all the data in all 4 transactions. Figure 9.2 shows how the root is calculated by pairwise hashes of the nodes. Because the Merkle tree is a binary tree, it needs an even number of leaf nodes. If there is an odd number of transactions to summarize, the last transaction hash will be duplicated to create an even number of leaf nodes, also known as a balanced tree. This is shown in figure 9.3, where transaction C is duplicated. The same method for constructing a tree from 4 transactions can be generalized to construct trees of any size. In Bitcoin, it is common to have several hundred to more than 1,000 transactions in a single block, which are summarized in exactly the same way, producing just 32 bytes of data as the single Merkle root. In figure 9.4, you will see a tree built from 16 transactions. Note that although the root looks bigger than the leaf nodes in the diagram, it is the exact same size, just 32 bytes, whether there is 1 transaction or 100,000 transactions in the block. The Merkle root always summarizes them into 32 bytes. To prove that a specific transaction is included in a block, a node only needs to produce log 2n 32-byte hashes constituting an authenticating path or Merkle path connecting the specific transaction to the root of the tree. This is especially important as the number of transactions increases, because the base 2 algorithm of the number of transactions increases much more slowly. This allows Bitcoin nodes to efficiently produce paths of 10 or 12 hashes, 320 minus 384 bytes, which can provide proof of a single transaction out of more than 1,000 transactions in a megabyte size block. In figure 9.5, a node can prove that a transaction K is included in the block by producing a Merkle path that is only 4 32-byte hashes long, 128 bytes total. The path consists of 4 hashes shown with a shaded background in figure 9.5, HL, HIJ, HMNOP and HABCDEFGH, with those 4 hashes provided as an authentication path. Any node can prove that HK with a block black background at the bottom of the diagram is included in the Merkle root by computing 4 additional pairwise hashes HKL, HIJKL, HIJKL, MNNOP, and the Merkle tree root outlined in a dashed line in the diagram. The code in example 9.4 demonstrates the process of creating a Merkle tree from the leaf node hashes up to the root using the libitcoin library for some helper functions. So this is the output. Example 9.2 shows the result of compiling and running the Merkle code. Example 9.2 compiling and running the Merkle example code. The efficiency of Merkle trees becomes obvious as the scale increases. Table 9.3 shows the amount of data that needs to be exchanged as a Merkle path to prove that a transaction is part of a block. As you can see from the table, while the block size increases rapidly from 4 kilobytes with 16 transactions to a block size of 16 megabyte to fit 535 transactions, the Merkle path required to prove the inclusion of a transaction increases much more slowly from 128 bytes to only 512 bytes. With Merkle trees, a node can download just one block header, 80 bytes per block, and still be able to identify a transaction inclusion in a block by retrieving a small Merkle path from a full node without storing or transmitting the vast majority of the blockchain, which might be several gigabytes in size. Nodes that do not maintain a full blockchain called Simplified Payment Verification SPV nodes use Merkle paths to verify transactions without downloading full blocks. So I'm going to leave it here today for this video. If you like listening, please consider like, sharing and subscribing. Thank you.